Before we get started on the examples and notes for day 18, there are a couple more basic trig identities that we need to talk about. So first thing we're going to do is talk about one of the major trig identities, which is called a Pythagorean identity. So first I'm going to draw our unit circle here. So if I have some angle theta here, and doesn't have to be specific to quadrant 1, just picking an angle there, the coordinates of that angle are cosine of whatever the angle is, sine of whatever the angle is. So if I draw the corresponding triangle here, the side lengths are x, which is the side along the x-axis, is cosine of theta, and the y value is sine of theta. And remember, our unit circle is called the unit circle because it has the equation x squared plus y squared is 1. So the first major trig identity, and is one of the most important trig identities, is called the Pythagorean identity, and it really has to do with the Pythagorean theorem and a triangle inside of our unit circle. So if we have a triangle, and a right triangle specifically, and we want to find the side lengths, we can use the Pythagorean identity to do that. So if you think about the side lengths of the triangle we have drawn here, if one side is cosine of theta, the other side is sine of theta, and the hypotenuse is 1, because it's the unit circle, I can set up a Pythagorean theorem or Pythagorean equation for the side lengths of that triangle. So sine of theta is the side opposite the angle, and I want to square that, plus cosine of theta, which is the side adjacent to the angle, squared is equal to 1 squared. So there is one bit of notation here that we have to be aware of. So if I square sine of theta, like how do we write that, or what does that look like? And the way you write sine of theta squared is actually sine squared of theta, and then it'd be plus cosine squared of theta equals 1. And the reason why the squared goes in between the sine and the theta is because the angle isn't being squared, but instead of having to write the entire sine of theta in parentheses with the squared outside, we write it as sine squared of theta, which means the exact same thing. It's just a lot cleaner and faster way to write it. So this identity here, sine squared plus sine squared of theta plus cosine squared of theta equals 1, is one of the most important trig identities that we'll deal with. With this trig identity, this Pythagorean identity, there are a couple different ways we could write it, meaning sine squared of theta plus cosine squared of theta equals 1 is one of the most common ways we'll see it, but if I wanted to kind of rearrange the terms, there are alternate forms in which this theorem can be written, and that's going to come in handy when we start simplifying some trig expressions in the notes. So if I wanted to rewrite this identity so that sine squared of theta was by itself, what I would need to do is subtract cosine squared of theta from both sides, and this is an alternative form of the exact same identity. And if I wanted to write the identity with cosine squared of theta by itself, I would subtract sine squared of theta from both sides from the original, and I would get 1 minus sine squared of theta. So those are just two additional ways to write the exact same trig identity, just getting one of the terms by itself. In addition to the Pythagorean identity that we just identified, there are a few other ones that we need to talk about in terms of simplifying expressions. We talked about most of these yesterday, which is what we call the reciprocal trig functions or reciprocal trig identities. So if I want to identify sine of theta, sine of theta can be thought of as 1 over cosecant of theta, or the way we wrote it yesterday, we defined cosecant of theta as the reciprocal of sine. Both of those are equivalent, and we'll be using those identities to be simplifying some expressions. So sine of theta is 1 over cosecant of theta, or cosecant is 1 over sine. And then cosine can be thought of as 1 over secant of theta, or secant can be thought of as 1 over sine or cosine of theta. So that's similar to what we talked about yesterday. I just want to kind of get them identified kind of up front, because we're going to be using these to make some simplifications. Tangent of theta is 1 over cotangent of theta, or cotangent of theta is 1 over tangent. Now there's only two more that we need to talk about, and that is tangent of theta can also be thought of as sine of theta over cosine of theta, and we talked about that when we were finding the values of tangent around our unit circle a few days ago. And then because tangent of theta is sine over cosine, that means cotangent can be thought of as cosine of theta over sine of theta. So those are the basic trig identities that we need right now to be simplifying some expressions that we're going to get to in the notes. So for these notes, we are going to be doing, for the cleanest way that I can describe it is, we're going to be doing some simplification using the same kind of algebraic rules we've been simplifying expressions throughout our high school career. So if you look at example 1a, if I want to simplify that, it's going to be a combining like terms kind of problem. If you look at example B, I have some binomial being squared. That looks a lot like us multiplying things out or squaring binomials. So the same algebraic rules are going to apply when we simplify. We're just going to be using that in the context of sine, cosine, tangent. So we're going to use some of our algebra rules to make some simplifications here. So if you look at example A, kind of already talked about it, some combining like terms, but what you should see there is if I have sine of theta plus 2 cosine of theta minus 4 cosine of theta, 2 cosine of theta and 4 cosine of theta are like terms. So if I want to simplify, I want to combine like terms, I would literally just subtract the coefficients there. So what I would get is sine of theta would stay by itself since there is no other like term that can be added or subtracted to it. And then 2 cosine of theta minus 4 cosine of theta would give me negative 2 cosine of theta. So in terms of simplifying that, that is the simplified version of that expression. Treat it just like we did with algebra with combining like terms, where cosine of theta is all together attached, and I'd just be looking for ways to make a combination of two terms there. Now if you look at example B, I have a binomial squared, so sine of x plus cosine of x quantity squared, and if I want to multiply that out, one way to do it is to write that binomial twice and then double distribute, or you might call it FOIL. So if I do that, sine of x times sine of x is sine squared of x. Remember that squared in between the sine and the x is just saying we're squaring the whole thing. We just don't write sine of x all in parentheses squared every time. So this is just notation that is a little bit more straightforward and easier to write. And then sine of x times cosine of x would give me sine of x cosine of x. And then if I do cosine of x times sine of x, I would get sine of x cosine of x. And then the last term would be cosine squared of x. So if I look at that, now I have 4 terms, and if I want to simplify, I'm looking for ways that I can use some of the identities that we just identified or combine like terms, something like that. So if you look, I have sine squared of x, and then that last term is plus cosine squared of x. And one of the identities we identified is sine squared plus cosine squared is 1. So I can rewrite those two, add them together. If they're added together, I can replace that with just 1. And then the middle terms, sine of x, cosine of x plus sine of x, cosine of x, those are like terms. So if I add them together, I get 2 sine of x, cosine of x. So that binomial squared gives me 4 terms, and then the sine squared plus cosine squared becomes 1. That's one of our identities. And then sine of x, cosine of x plus sine of x, cosine of x add to 2 sine of x, cosine of x. So if you look at example 2, slightly different kind of setup here. I have cotangent of t, cosine of t, and tangent of theta, cosecant of theta. And the strategy we're going to use to make some simplifications here will be to kind of rewrite everything in terms of sine and cosine. So a lot of our identities are related to sine and cosine. So if I can make a substitution or rewrite these in terms of sine and cosine, then I might have something that I can simplify. So if you look at example A, we're actually going to adjust this example slightly, and I want to call it cotangent of t times sine of t rather than cosine. You'll see why when we get to simplifying. It's not that the problem before was wrong, it's just a typo there. So I want to call it cotangent of t sine of t. So when we say rewrite in terms of sine and cosine, what I'm going to do is replace that cotangent of t with cosine of t over sine of t. So just rewriting cotangent in terms of sine and cosine, and that's going to be multiplied by sine of t. So if I want to simplify this, actually the two sine of t's will reduce, and all I'll be left with is just cosine of t. So that's example 2a. First rewrote everything with sines and cosines, and then looked for ways that I can simplify this by reducing or maybe factoring, combining like terms, all those algebra techniques we've learned before. We're just going to apply them to using them with trig functions. So if you look at example 2b, I'm going to rewrite tangent of theta as sine of theta over cosine of theta, and I'm going to rewrite cosecant of theta as the reciprocal of sine of theta. So that's just me changing those two sines and cosines. Now if I want to simplify here, the sine in the top on the left fraction and the sine in the bottom of the right fraction will reduce. So what I'll be left with is 1 over cosine of theta, which can be written as one of the functions we already talked about, which is secant of theta. So if you take a look at example C, looks like it has a little bit more going on. I have cosine squared of t minus 1 in the top and sine squared of t in the bottom. So what I'm going to do here is just kind of rewrite that trig identity that we identified already. And sine squared of t plus cosine squared of t equals 1. What I'm going to do is try and rearrange that so that it looks exactly like the numerator of my original expression. So I'm basically going to take that identity and kind of move some terms around to try and make it the same as the numerator so that I can substitute. So if I wanted to move some terms around, if I took that identity and subtracted 1 from both sides, that would get my 1 on the same side as my cosine squared. Subtracted sine squared of t from both sides, I would get the same identity, just kind of rearranged. So cosine squared of t minus 1, which is the same as my numerator in my original fraction, is equal to negative sine squared of t. So what I'm going to do with that is replace my numerator with negative sine squared of t, and then that would be over sine squared of t. So now if I want to simplify that, actually the sine squared of t in the top and bottom will reduce, but that negative is still there. Be careful. So that would leave me with an answer of negative 1. So the idea there is using that trig identity that I have, making a substitution so that something can reduce or cancel or combine like terms. Those same things we're going to be looking to do, but I had to make a substitution here. So we take a look at example D, or problem D there. The top, the numerator, looks a lot like one of my trig identities, cosine squared of x plus sine squared of x. The only problem is each of them has a coefficient of 2. So what I'm actually going to do in this case is factor out that coefficient of 2. So that would give me the expression 2 times the quantity cosine squared of x plus sine squared of x all over 2 secant squared of x. Now what I'm going to do with that is, now that I've factored out my 2, what's inside of my parentheses is actually my trig identity. So that becomes a 1. So I have 2 times 1 in the numerator, which is 2, over 2 secant squared of x. The 2's can reduce, so I'm left with 1 over secant squared of x. And if secant is the reciprocal of cosine, then secant squared is the reciprocal of cosine squared. So my final answer here would be cosine squared of x. So I had to factor out a 2 in the numerator so that I can substitute using one of my identities, and then simplified from there. And cosine squared of x can't be simplified any further. So let's take a look at example 3. This is kind of a slightly different type of problem here. So if you look, what we're asked to do is give exact values for 5 of our trig functions, and what we're given is what the value of tangent is. Tangent of theta is 1/4, and that 0 is less than or equal to theta is less than or equal to pi over 2. What that really is just a little bit of information kind of telling us which quadrant that our angle can be found in. So I don't know exactly what the angle looks like. It's just some angle between 0 and pi over 2. Telling me where my angle is located is going to give me an idea whether my sine, cosine, tangent, secant, cosecant, cotangent is positive or negative. Now, because I'm in quadrant 1, If you remember our all students take calculus acronym going around the unit circle, anything in quadrant 1, everything's positive. So sine, cosine, tangent, secant, cosecant, cotangent, they're all positive. So what I'm going to do here is I'm going to draw a little reference triangle using the information that I was given. So if you remember SOHCAHTOA, that's going to be kind of how we approach this problem. So tangent of theta is 1/4, that was given to us. So what I drew is just a little triangle here in quadrant 1 where theta is that reference angle. So tangent is really the opposite side over the adjacent side. So if tangent is 1/4, what I can do with that information is actually say that the opposite side of theta is 1 and the adjacent side of theta is 4. So in order for me to complete this triangle, I have to find out how long the hypotenuse is. Now here's the difference in this problem. When we're on the unit circle, the hypotenuse is always 1. But in this context, in order for tangent of theta to be 1/4, the hypotenuse can't be 1. Because if the opposite side is 1 and the adjacent side is 4, the hypotenuse is supposed to be the longest side. And if I put 1 there, it wouldn't be. So this type of problem, I'm not necessarily on the unit circle, but I'll still be using the same kind of relationships of sine, cosine, and tangent to find these values. So how do I find my third side of my triangle? Well, if it's a right triangle, I'm going to use the Pythagorean theorem. So I have 4 squared plus 1 squared equals c squared, and c squared, I'm just calling that the hypotenuse, keeping my notation consistent with the Pythagorean theorem. So I would get 17 equals c squared, so my hypotenuse is the square root of 17. So what we're asked to do in this problem is find the other 5 trig ratios, or trig values. So those would be sine, cosine, secant, cosecant, cotangent, because I was already given the value of tangent. So what I'm going to do here is just write a spot for basically the other 5 trig functions so that I can calculate them. So if I want to find sine of theta in this triangle would be the opposite side of the angle over the hypotenuse. So in this case, it would be 1/√17, and then I would have to rationalize that, and I'd get multiplied by √17 over √17. So sine of theta in this triangle is √17 over 17. Now, if I want to find cosecant of theta, remember cosecant of theta is the reciprocal of sine of theta. Now, instead of taking the reciprocal of √17 over 17, which you can do, but then you'd have to rationalize, I'm actually going to think of the unrationalized version of sine, which is 1/√17. The reason why I would pick that one is when I flip it, my radical would be in the top, and I wouldn't have to rationalize anything. So what I'd get is, when I flip 1/√17, I just get √17. So cosecant of theta would just be √17, and I wouldn't have to rationalize. Now, if you used the value for sine that I put in the red box there, and then flipped it and rationalized it, you'd get the exact same value, but it would just create a little bit more work for yourself. Going back to the triangle, if I want to find cosine of theta, it would be the adjacent side over the hypotenuse, which is 4/√17. And then I would rationalize, multiply the top and bottom by √17. So my cosine value would be 4√17 over 17. And then similarly, for secant of theta, I'm not going to use my final answer I got for cosine. I'm actually going to go back to my original value, which is 4/√17. And I'm going to take that number and flip it over, which means secant of theta would just be √17 over 4. So I have those 4. And then if I want to find cotangent, there's a couple ways you can go about it, but you could go back to your triangle and set up a ratio, but know that if tangent was given to us, and tangent is 1/4, that means cotangent is the reciprocal of that, which is 4. In our last example here, example 4, is a similar context. I am going to make a couple slight adjustments to the problem, so just kind of follow along with me. Instead of going to look at an angle in quadrant 1 like we did in the last example, I just want to kind of change it up a little bit. So I'm actually going to make the interval 3 pi over 2 to 2 pi. And all that does is take my angle, instead of putting it in quadrant 1, it's going to put me in quadrant 4. And then if I'm in quadrant 4, that means my sine value is negative. So those are kind of the two adjustments I'm going to make to the original problem. And then I'm going to draw a similar triangle as the previous example, put it in the correct quadrant, find the side lengths, and then use those side lengths to find our two trig ratios that we've identified kind of down there in the bottom. So if I draw my triangle, I'm in quadrant 4 somewhere. And again, you don't have to be super specific about the angle because we actually don't know the angle, but drawing our triangle and labeling the side lengths is going to be really important in this case. So if I draw my triangle, I'm going to put theta as my reference angle. It's going to be between the terminal side of the angle and the x-axis. Now, in a triangle like this, a right triangle, sine of an angle would be the opposite side over the hypotenuse. So I can use this fraction actually and call negative root 3 the opposite side of the angle. And negative in this case makes sense because I'm below the x-axis. Now that doesn't mean the side length is negative, it just means the length is root 3 but in the negative direction. So that's why that has to be negative, because if you forget that negative, it's going to throw off your value for cosecant and cotangent for sure. So then the hypotenuse is 2. And in order for me to have my third side, I would need to set up a Pythagorean theorem. So I would write negative root 3 quantity squared plus b squared, where b is the other side, and that's going to be equal to 2 squared. Which means 3 plus b squared equals 4. So that means b squared is 1. So my other side length is 1. So I have a triangle, a right triangle with side lengths 1, negative root 3, and 2. So I'm going to use this triangle to find the values of cosecant and cotangent. So if I want to find the value of cosecant of theta, I'm first going to find the value of sine of theta. So this one was actually given to me. So if sine of theta is negative root 3 over 2, that means cosecant of theta would be negative 2 over root 3. And the only thing I would need to do to that value is to rationalize and simplify. So to rationalize this, I'd multiply the top and bottom by root 3 over root 3, which would give me the value negative 2 root 3 over 3. So that's the value of cosecant in quadrant 4 using this triangle as a reference for the ratios that I'm looking for. And then the last one would be cotangent. So cotangent of theta, I'm first going to find tangent of theta, which would be the opposite side, which is negative root 3, over the adjacent side, which is 1, opposite over adjacent. So I get tangent of theta equals negative root 3, which means cotangent of theta would be the reciprocal of that, which is negative 1 over root 3. And then in order to simplify that, I would need to rationalize my fraction. So I'd multiply the top and bottom by root 3. And then that would give me negative root 3 over 3. So cotangent of theta in this context, in this triangle, in quadrant 4, would be negative root 3 over 3. So these last two problems are ones where we have to take kind of the values of our trig functions and our Pythagorean theorems and kind of put it in a context where we can find these ratios. The examples at the beginning were just pure algebra simplification, so that's the notes for day 18. Your homework is the worksheet that you grabbed in class today, and we will talk about our homework next time we meet.